Hello everyone, this is 3.2 for Calculus 1, and this is a discussion on product and quotient rules. Similar to how we saw rules from the previous section, we'll be seeing new rules now, and these rules are a little more involved, but they're honestly not too bad. You just have to remember them. Of course, they'll be given to you, but we use them so often they're kind of embedded in our brains anyways, at least they will be shortly. But let me just say the product rule is this. So d over dx of f of x times g of x, so derivative of a product of two functions, is f prime times g plus f of x times g prime of x. In shorthand, we say u v all prime is u prime v plus u v prime, where u and v are functions of x. The chant that I often say out loud when actually applying this is the following. Derivative of the first times regular of the second plus regular of the first times derivative of the second. Okay, now since it's addition, it doesn't actually matter which order you do it in, but I always do derivative of the first as the first term. And you'll see why once we get to quotient rule, it allows us to relate the two more easily. A very common mistake that people make that obviously I don't want any of you to make is this. Derivative of a product is just a product of derivatives. That is not true. Though it is true with addition and subtraction, you can just take derivative term by term if it's addition or subtraction. It's not true with multiplication or even division, as it turns out. And here we're going to do an example. I'm going to actually do this two different ways just so we can believe the product rule, because I'm not going to prove the product rule. It can be done. You can try it on your own, and you can even look in the book. The book does it basically right off the bat on chapter 3.2. They prove the product rule. It's not too bad. It uses definition of derivative just like you might assume it might, and it does. But instead what I'm going to do is I'm going to do this two ways. One way that we know and we've already kind of assured ourselves of that it works, and then this new way we're going to compare that the same, and that should be convincing enough that this rule always works for products. So first, let's do it the way we're used to. To do it the way we're used to, we have to FOIL it first. So we multiply everything by x and then everything by 3, we get the following. 2x cubed minus x plus 6x squared minus 3. And this is just f of x. We haven't even taken the derivative yet. Now, taking the derivative, term by term using power rule throughout, will give us 6x minus 1 plus 12x, and then negative 3 goes to 0. So this is my answer in no particular order. The terms aren't in any specific order. Also this was 6x squared. If I wanted to write it in order, in descending order, let me do that. I'm going to rearrange these and write 12x first and negative 1 second, if that's okay with everyone. Well, if it's okay with you or not, I did it regardless. It's fine. And now I'm going to erase this and then use the product rule to see if we get the same thing, but I'll leave the answer, of course. Alright, so I've erased things and moved our example back up. This is the answer we got. Let's see if we can get the same thing using the product rule. So just to recall, the product rule is this, and I'm going to use that chant I was talking about earlier. So to jump into derivative, when we have derivative of a product of two functions like we do here, we can just use the product rule. Derivative of the first, derivative of x plus 3 is just 1 plus 0, so that's 1, times regular of the second, so leave this one alone, plus regular of the first now, so now leaving x plus 3 alone, but then multiplying that by derivative of the second. Derivative of 2x squared is 4x. Derivative of negative 1 is 0, so it's just that. And again, derivative of first, regular of the second, plus regular of the first times derivative of the second. Now, this may not look the same because we have to simplify a little bit in this case, but let's do that. Here, there's nothing to distribute because 1 times anything is itself anyways. So that's 2x squared minus 1, plus, that's going to be 4x squared plus 12x. These will combine to 6x squared, and if we write it in order, we get 6x squared plus 12x minus 1 as our derivative function. And is that the same as what we got earlier the other way? Yes, they are indeed the same, and they should be. If not, then the product rule will be false, or we did something wrong. So that's kind of nice. Now we'll see a few other examples right now that you can't do another way. So now we'll take a look at some functions that we couldn't take the derivative of without knowing the product rule. Alright, so here are some nice examples that we'll use product rule on. And notice we couldn't find the derivative of at least the first two without knowing the product rule. and this is how you do it. So for the first example here, it's going to be derivative of the first, regular of the second, plus regular of the first times derivative of the second. So notice here, when I say first and second, I'm talking about the first part of the product and the second part of the product. So I'm taking the derivative of the first, leaving the second alone, then leaving the first one alone and taking derivative of the second. Now as it turns out, since e to the x has derivative being itself, it looks like it's unchanged when in reality we took its derivative there. I'm going to simplify a little bit, but in reality it's nothing too crazy, it's just this. I'm just not writing that one, basically. Now if you wanted to factor e to the x out, you certainly could, but I'm going to leave my answer non-factored. The reason why I'm at least bringing this up, though, is because when we see after this example right now, these examples right now, after we see quotient rule, we may actually need to do something like this because there may be cancellation, but we'll get to that in its own time. I'm just bringing that up right now that you could factor if you wanted to for product rule, but you don't have to for product rule. Okay, same thing here. If we distribute first, that's actually a terrible idea. The reason why it's a terrible idea is because if we were to distribute first, you would get this. I'm just going to do it just to show you what happens. And you'd have to do a product rule for each of these. So you'd have to do two product rules, basically. So instead of doing that, instead of doing two product rules, I'm going to just do this. As is. So I got my first and second set out. Derivative of the first is 3x squared plus 2x times regular of the second plus what? Right, regular of the first and then derivative of the second. But again, what's the derivative of e to the x? Yes, it's e to the x. Then we can distribute and combine any like terms, but there aren't any. In fact, it may not be super obvious, but I'm going to pull out e to the x from both of these big terms here, and pulling e to the x out of everything will leave only these on the inside. So only these left on the inside in order will be x cubed plus 3x squared plus 2x plus 2. And that's just me writing it in descending order, just so we're kind of consistent about things. And yes, this is the answer for the second example. Okay, great. Now, this one is kind of funny, because this one you can actually do without using the product rule, because it's just a constant multiple rule. The constant multiple rule says that the derivative of a constant, let's say 5 times e to the x, any function, is just that constant times the derivative of that function. So the answer here is going to be 5 times derivative of e to the x, which is just itself 5x. Now, I'm going to use product rule here just to show you that you can. So remember, there's first and second part of the product. So derivative of 5 is 0 times regular of the second e to the x plus 5 regular of the first times derivative of the second, which is e to the x. Now notice, in the first term, anything times 0 amounts to 0. So all we're left with as our derivative is 5e to the x, exactly what we expected it to be. And this is one way you can actually use the product rule to convince yourself of the constant multiple rule. Because since the derivative of any constant on its own is 0, then the first term in the product rule is going to be 0. And then you just get regular of the constant times derivative of the other non-constant function. So there you go. And now we're going to move on to quotient rule. Okay, so now very similar to what we saw in the product rule, we'll see with the quotient rule. The quotient rule has this rule. Derivative of a quotient of two functions, a fraction of two functions, one divided by the other, is f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. The shorthand notation is u over v all prime is u prime v minus uv prime all over v squared. And we can kind of see now why I chose to write product rule in that order, taking derivative first, when in reality I said it doesn't matter which order you actually do it in practice. In the quotient rule, the order does matter on top, because notice, it's f prime of x times g of x minus f of x g prime of x. Since it's subtraction, you can't mess with the order. With product rule, it was addition, so you could mess with the order, but the reason why I chose to write it in that specific order was so that it translates nice into quotient rule. And I say for the chent here, instead of first and second, there's top and bottom. So I say the following. Derivative of the top times regular of the bottom minus regular of the top times derivative of the bottom all over the bottom squared. And now we're going to, just like we saw with product rule, we're going to see an example that we could do a previous method and then compare it to quotient rule to make sure the quotient rule is, to convince ourselves that it's okay, because I'm not going to be proving it. So here, how would we do this normally? Well, we would split it up as each term on top divided by the common denominator. Just like that. Then rewrite them as individual powers. So t squared over t squared is just 1. Minus 2t over t squared is 2t to the negative 1. Plus 3 over t squared is 3t to the negative 2. Then we can take the derivative. So f prime of, this should be f of t, sorry, not f of x. So there we go. So f of t then is what? It's derivative of 1, so derivative of each term. Derivative of 1 is 0, so I'll write it though. So 0 plus, well, this is negative 2 times negative 1 because of the power rule, negative 1 drops down, so it's positive 2 t to the negative 2 because negative 1 minus 1 is negative 2. Bringing the negative 2 down, negative 2 times 3 is negative 6, so minus 6. T to the negative 2 minus 1 is negative 3. Now, of course, we don't care about that 0, so this is f prime, by the way. So f prime of t altogether with no negative powers now is 2 over t squared is what I meant to say, minus 6 over t cubed. And if you want to find a common denominator, you can multiply the first one, top and bottom, by t, and altogether this will give us what? It'll give us 2t minus 6, all divided by t cubed now. Good? So this is the answer for our derivative. And now I'm going to clean this up, do the same example but with the quotient rule now, and compare it to the answer we just got using previous known methods. Alright, great. So I've had everything cleaned up here, and this was the answer we just got. And let's try to apply the quotient rule now. So we can just jump straight into the derivative. It's going to be all over the bottom squared. So I always kind of do that first. And then on the top, it's basically the product rule, but with a subtraction instead of addition. So that's derivative of the top. Derivative of the top is 2t minus 2 plus 0, but I'm not going to write it, times regular of the bottom, minus regular of the top. So rewrite the top. But now times derivative of the bottom. Derivative of the bottom is 2t, as we can see. Perfect. So now, notice the denominator t squared, it says all over the bottom squared. T squared squared is just t to the 2 times 2, so that's 2 to the 4th total. Let's distribute the t squared and the 2t and the negative, so keep that in mind. So there's like 2 distributions to do on the second part. But anyways, here we get 2t cubed minus 2t squared minus 2t times t squared is 2t cubed. Negative distributed here to the second term is positive. 2t times 2t is going to be 4t squared. Negative times this is negative 3, but that times 2t is going to be negative 6t. Good? Great. So now combining terms, like terms, these are like terms, they actually cancel out, funny enough. These are like terms. Negative 2t squared plus 4t squared is 2t squared. Then we have minus 6t all over t to the 4th. And now, like I said, we can factor from the top. What do the top two have in common? They have 2t. But pulling out 2 is not going to do anything as far as cancellation goes. Pulling out t will, because it'll cancel with this t to the 4th. And in fact, we can see that if we pull out t only, we'll have 2t minus 6 left on top. And then after cancellation, t goes into t to the 4th. t to the 3 times, I guess you can say. So we're left with exactly what we got before. 2t minus 6 all over t cubed. Okay, so now again, just like with the product rule, we're going to take a look at a few examples now that we couldn't do by other methods before. Okay, so now for these next examples, the first one, x e to the negative x, though it looks like a product, it's written like a product, as a product, we can't actually use product rule here. And the reason why is because if we just try it, derivative of the first is 1, regular of the second is e to the negative x, that's fine. But then plus, regular of the first is x, but now what's the derivative of e to the negative x? It's not itself, as it turns out. Derivative of e to the x is itself, derivative of e to the negative x is something a little bit different, and it's hard to do from what we know right now. So instead what I'm going to do for you is I'm going to write this as x over e to the x, because now we can take derivative of each one of these, and since it's a quotient, we'll have to take derivative of the whole thing using quotient rule. So now using the quotient rule, what we get is y prime is equal to all over the bottom squared, derivative of the top times regular of the second, minus regular of the top times derivative of the second. When I say second, I mean bottom. And notice that on top, they both have e to the x in common. So pulling that out gives you e to the x times 1 minus x. If you distribute e to the x back, you get exactly this. So that makes sense. And in the denominator, this is really e to the x times e to the x, which is really e to the 2x. But the reason why I'm writing it like this, of course, is because we're going to cancel. Notice e to the x's cancel. So we're just left with our answer finally, 1 minus x all divided by e to the x. Good. Next one here, again, it's a quotient of functions, so we're going to apply the quotient rule. So to get g prime of x, we're just going to do what we've been doing. All over the bottom squared, so keep that in mind. And I always do that first, but you can do it after, it's fine. I just like doing it like that so I get my fraction set up. Derivative of first, right? So you do derivative first, top, bottom. So derivative of the top is just 2, right? 0 plus 2, times regular of the bottom, 3 minus 4x, minus regular of the top, 1 plus 2x, times derivative of the bottom. Now derivative of 3 is 0, derivative of negative 4x is negative 4, so derivative of the bottom is just negative 4. Good. And now of course there's a double negative here. It's negative times negative 4, so that's double negative. So now what we need to do is distribute 2 on top, distribute 4 on the bottom. Distribute 2 in the first term, 4 in the second term is what I meant to say. And let's see what we get. So now we get g prime of x is equal to all over 3 minus 4x all squared. We get 6 minus 8x plus 4 plus 8x. Look at that. The 8x's actually cancel out, funny enough, and we're left with 10 on top only. So our answer then is 10 over 3 minus 4x quantity squared. And there's no cancellation here. So this is it fully reduced, basically. And now on to the next one. Now, I tried checking, and the bottom can be factored. It's hard to do, so I'm not going to do it. And the result won't be able to be reduced anyways, even though there are things that you can factor. But in any event, let's just follow the quotient rule blindly, so to speak, and see what we get. So we get y prime is equal to all over the bottom squared. So it's going to be a lot. Hopefully we have enough space here. I think we have enough space, but let's see. Derivative of the top is 2t. Let me try to squeeze it in just in case. Regular of the bottom is t to the 4th minus 3t squared plus 1, close parentheses, good, minus what? Well, now minus regular of the top, so that's t squared plus 2, times derivative of the bottom. Derivative of the bottom is 4t to the 3rd minus 6t plus 0, so I'm not going to write that 0. So 4t to the 3rd, just barely making it, minus 6t. Come on. Close parentheses. Perfect. Whew. Nice. So there's a little bit of distribution here. We need to FOIL, but then distribute the negative as well. So I'm going to distribute the negative and, well, yeah, I'll distribute the negative first, then I'll FOIL after, I guess. It's going to be a lot, though. You know what? Let me do this. Let me distribute the negative and rewrite this as plus negative t squared minus 2, and then we can FOIL for the second part of that on top. So y prime is equal to all over the bottom squared okay. Distributing the 2t, we get 2t to the 5th minus 6t to the 3rd plus 2t. And now let's try to FOIL this out. Let's see what we get here. We get negative t squared times 4t to the 3rd is negative 4t to the 5th. Okay. Negative t squared times negative 6t is positive 6t cubed. Okay, two more. Distributing negative 2, we'll get negative 8t cubed. And finally, positive 12t. Okay, good. Extend this. Okay, combine like terms. Let's try to underline the like terms, or I guess I'll dot the like terms on top. So for the fifth powers, we have 2 minus 4. That's going to be negative 2. For the third powers, I'm going to double dot that. Oh, look at that. The 6t cubes cancel, so we're only left with negative 8t cubed. That's nice. And now let me triple dot the t's, just to kind of keep track of what we're doing here. And those will add up to 14t. So I think we probably have space here. So now our answer, y prime, is all over this squared. So t to the 4th minus 3t squared plus 1 quantity squared. Okay, sorry about the spacing there. Hope you can see that. And then on top, we have the t to the 5th combined to negative 2t to the 5th minus 8t cubed. Good. And then plus 14t. And that's my answer. Let me box that. Perfect. Now again, you can try to factor the top and factor the bottom and see if anything cancels. And I'll just tell you right now that nothing cancels. I tried it already. And that concludes 3.2. I hope you enjoyed the video. It was a little more technical than what we saw last time, but in reality, it's just using things we used last time with these new rules. And there are only 2 rules I showed you here compared to like the 5 we saw from 3.1. Great. So now we'll move on to 3.3 in the next video, and I'll see you then. Thanks for watching.